We can't talk about pulmonary function testing without also discussing quality assurance. Anytime you are doing testing of anything from the body, whether it be taking tissue out and running tests on it, taking blood out, running tests on it, or measuring lung volumes and flows, etc., we have to have some mechanism to assure that what we're doing is accurate. We're dealing with flows, we're dealing with volumes. We have to do some type of calibration. When we're doing blood gases, which is often done in a pulmonary function lab as well, we have to do calibrations and quality assurance testings to make sure that our analyzers are measuring all of these things appropriately. Some of the methodologies of quality assurance is that we look at the equipments and we do specific calibrations, and then we test them to make sure that those calibrations are accurate. So we'll analyze a certain gas that we're using, and then the analyzers will test and make sure that that's accurate. Or we will hook up a 3-liter syringe and put air into a machine, and we'll make sure that that value that the machine is analyzing is at or close to that 3-liter amount. Some of the maintenance that we have to do when these things go out of control is we might have to replace some parts. We might have to change some flow transducers. Sometimes manufacturers actually make us replace certain parts even if they seem to be working fine at certain time intervals. We have to have some control mechanisms, again, to make sure that when we're calibrating these things that they are calibrating accurately. And how do you do that? You test it. We use volume calibrations, a 3-liter syringe. We use gases to calibrate. We use liquid controls on a blood gas machine to test the gas calibrations. We use different things to test the pressure that's generated. We have it calibrated a certain way, and we do various tests to make sure that those things that are calibrated are accurate. How do we actually obtain or perform quality control, QC or QA quality control, quality assurance? You can do biologically. You can test a certain group. For example, how do we know that somebody is within their predicted normals? How do we determine what their predicted normals are? Well, they took so many people that were the exact same age and the same height, the same sex, the same race, no diseases, nothing like that, and they would do test after test after test, and based on that, they determined what the predicted normals are. We can do the same thing when we're looking at doing a QC on certain machines. We test normal subjects, or we compare to their previous when they don't have a disease. We can use what's called an isothermal lung analog testing. We'll talk about that a little bit more later on. We can do some comparisons of dilutions to body plasmography. We can also do some comparisons with chest x-rays. So, for example, if we were to do a helium dilution test and we compare it to body plasmography, and we see if there's a normal healthy adult, they really should be pretty accurate and close to one another because healthy adults do not air trap. If it's a normal healthy adult, remember body plasmography is pretty darn accurate even if they do air trap. You can compare the values you're getting with the machine to lung volumes looking at the chest x-ray. If we want to look at our calibration and QC spirometers, well, how do we do that? Well, we use a 3-liter syringe and we adjust the flow delivery. We will deliver it really fast. We'll deliver it really slow. And it should meet within this certain range. There's always a plus or a minus when you're dealing with controls. They're never going to always be exact, like it's going to be an exact pH or it's going to be an exact volume. We have to allow for just some minute errors because we don't live in a perfect world. You open up a vial that has control for a blood gas machine, the second you expose it to air, it could have some slight changes, so we have to allow for that. Syringes may be adjusted at 3 liters, but humans are pushing that plunger back and forth, so there may be a few slight errors. So typically, if you're using a 3-liter syringe, it's acceptable if the volume is within 3% or 0.05 liters of the 3-liter syringe. So if they're not, you have to go back through and try to recalibrate and figure out what's going on. Maybe you have a leak in the system, something like that. Fortunately, today's machines are pretty good about kind of guiding you and telling you what might be the problem, so that's kind of nice. You don't have to do quite as much research or digging like you used to. Our flow sensors, there's actually a pump in a body plasmography, for example, that does a sine wave pumping that measures the consistency of both inspiratory and expiratory flow. So it'll push the air in and pull it out. It'll also check to see what kind of resistance there are. All machines have resistance. Anytime you put anything in front of your mouth to blow through it, you're going to have some resistance. Ideally, that resistance should not exceed 1.5 centimeters of water pressure. That's kind of the standard, so it should be less than that, so that you don't get that back pressure that can actually change your volumes or your flows that you're measuring. Some real common spirometer problems that can cause some of our QC measures to fail are things like cracks or leaks within the volume displacement drums, low water levels if you have water seal, worn bellows, obstructed or dirty flow tubes, leaks in tubes and connections. A faulty recorder timing can do it. Inappropriate signal corrections, your body temperature, pressure, saturated. Remember that when you're doing PFTs, we want to measure the volume in the body at body humidity and temperature. That's 37 degrees Celsius, 100% saturated. When you blow that air out into a room that's cooler, those values can change. So we have to be able to correct for those. We want to make sure that our software is adequate. There's not a hiccup in it. Today's world PFTs are all pretty high tech, and there's a lot of there's a computer system in all of them, and so we want to make sure that the software is working right, everything's calibrated right, and there's not a defect in the computer and software interfaces. Okay, so we talk about calibration. We can also look at analyzers and anything that analyzes a gas. So if you have a blood gas machine, it's going to analyze PO2 and CO2. Those are gases. So you've got to have some mechanism to produce samples that would be a certain way based on certain conditions when tested. The same thing can be said for helium dilution. You've got to analyze the helium. You're not going to know what you're starting with unless you analyze it, or how much oxygen you're starting with unless you analyze it. We actually do calibrations. Blood gas machines are a prime example of that, as is some of your PFT machines. 2-point calibrations are basically calibrating at high and low ends of acceptability. So to a 0 point and then the highest range that you would accept in any given situation. That's a 2-point calibration. Whereas a 1-point calibration is typically only calibrating to one range. 2-point calibrations do to 2, the low and the high range. Blood gas machines do 2-point calibrations every so often, and then periodically in between, it does a 1-point calibration. When we look at calibration, we look at things like what we call linearity. Are we able to produce the expected outcomes in a linear fashion? So these different graphs here, if you look at the graph over to the left, is showing what a true linearity line is. It goes straight across. A slightly variable linearity it's still linear, because here's a helium analyzer. It goes a little bit high and a little bit low from that linear line, but as long as it fits within the acceptable ranges, that is still considered linear. Now you have an example on the box to the right that shows you that one that's swinging way out of linearity. If it exceeds that particular setting of a high or a low, it's no longer linear. In this case, this one is not linear because it swung way out of the linear line and then eventually came back in again. This could be a problem and something that you want to look for. Sometimes as you're doing these calibrations, you'll start seeing a trend of something starting. It may still be within the right range, but it's trending outside of that range. You want to look for those things because those are signals.